Well, welcome everyone. Thank you for attending. And today we have the Electrochemical Society's Industry and Careers Day, which is hosted by the ECS Pacific Northwest Section. I'm Corey Cobb. I'm a faculty member at the University of Washington and the vice chair for the ECS Pacific Northwest Section. Shannon, if you could progress to the next slide. This is the ECS Pacific Northwest Section Executive Committee members. I'm the lead organizer for this event with Shannon as well. And we've organized a great panelist of people from both industry and national labs, as well as afternoon sessions. And this event is really geared towards students and early career engineers who are trying to understand how they can apply their skill set to jobs in electrochemistry. Shannon, if you could go to the next slide, that'd be great. This is today's agenda for the panel. There are also afternoon sessions, which we'll talk about at the end. But as I mentioned before, we have a great spread of different companies and national labs that will be speaking about the great work that their organizations do, as well as what they work on themselves. And they'll also highlight either their personal career path or what their organizations look for in successful job applicants. And with that, I'll pass things over to Shannon Reed, who's the Director of Community Engagement at the Electrochemical Society.
Good morning, everybody on the East Coast, or West Coast rather. Starting to be afternoon here on the East Coast. Like Corey said, thank you for that introduction. I am Shannon Reed. I'm the Director of Community Engagement for the Electrochemical Society. I help to manage all things membership, also continuing education, marketing and outreach, sections, student chapters, all that kind of good stuff. So lots going on in my area. And what I wanted to chat with you all today about, just briefly at the beginning of this webinar, are the student and early career membership programs that we have at ECS. We have a number of different opportunities for students to become engaged in the Electrochemical Society, whether that's through awarded student membership, student chapters, or early career membership. And so on the screen, you'll see that we have 4 different membership opportunities for students and early career researchers. The first 2 that I'd like to talk about are the awarded student members and the student chapter members. So awarded student membership is provided to students through an application process and is paid for by divisions, by their primary division, once the awarded student application is approved. So awarded student membership is no cost to students applying through that program, and that is similar to the student chapter membership program. And so student chapter members, as long as there is an active student chapter on their institution's campus, students are able to join those student chapters and then also join ECS as a student chapter member to receive all the rights and privileges of an ECS member. On the flip side of that, we also have a student member category. So if you are not able or don't meet the qualifications for the awarded student membership or the student chapter membership, you can join ECS for a highly discounted amount. Student membership for ECS is only $30, and that includes your $15 primary division dues, as well as the $15 membership fee. And then ECS began in 2020, after we did some market research, piloting an early career membership category. And while it's still in its pilot stage, collecting data, we are offering that to early career members within the electrochemical and solid state science community. That membership rate is $70. It includes your $55 membership fee and your $15 primary division fee as well. So regular membership to the society is $130 total. And then in addition to the overall membership cost, there's also section dues, and those can range anywhere from $0, depending on which section you are joining, to $10. And so we have 24, 25 sections throughout the world, and ECS Pacific Northwest Section was formed in 2020 and has been doing a great deal of activity since their start. So you all have been quite the rock star section, and I'm happy to be here today to talk a little bit more about membership. And so with that, knowing what the membership options are, I just want to touch on the benefits of joining ECS. And so from our research, we know that one of the most important or regarded benefits of ECS membership is going to be the access to the latest published research that's available in the ECS Digital Library, and that's housed on IOP Science. Second most, especially for our student and early career researchers, is the growth of their professional network. So I had mentioned the student chapter membership program. In 2020, we reached a milestone of 107 international student chapters. When I started with ECS in 2016, at the Prime 2016 meeting in Hawaii, we had just chartered our 50th student chapter. So we have had some exponential growth there in 4 years. And our student chapters are very active. We also have the 24 regional sections, including the Pacific Northwest section. And then we have 8,000 members throughout the globe. So this ECS is a really nice opportunity for students and early career researchers to get involved and also network with peers in their disciplines. Student members also receive significant discounts on things like biannual meeting registrations, short courses, and professional development workshops. And one of the things that I think is paramount to the success of students and early career researchers is our ECS Career Center. We launched that a few years ago. It's picked up some speed over the last couple of years, which has been great. It offers career planning resources and then job search functionality as well. And being a member of ECS alerts you to the new job postings that occur in the Career Center. So talking a little bit more about the student chapter program, again, I had mentioned we chartered our 50th student chapter in Prime 2016, and that's grown to 107 student chapters globally. One of the benefits of having a student chapter on your campus is that ECS provides student chapter funding. So if student chapters are hosting events, webinars, in-person meet and greets, doing some promotional material to do outreach in their community, ECS offers up to $1,000 in reimbursement funding for those types of events on your campus. And so that's a nice opportunity for our student chapters. I do want to highlight that there is a difference between section and student chapters. So student chapters are run and facilitated by students associated with college and university campuses. Sections are region-based. So if you are a member of a student chapter, that does not necessarily mean that you are a member of a section. And if you are interested in joining a section, we can help you join a section. You just have to email customerservice@electrochem.org or indicate it on any of the applications that you submit when you join as a member, whether that's awarded student or as a student or early career member. As a point of information, we have the ECS Student Center, which is a webpage on the electrochem.org website. It has information about each of the membership programs, as well as the ECS student chapter directory, so you can see where all of the student chapters are located. And then student members also have access to the ECS member directory. Then quickly, I just wanted to highlight some upcoming events for the ECS Pacific Northwest section. So there is a webinar on June 10th. With Dongjing from Idaho National Lab, and then Shannon Bocher in July 2020, followed by Bo Zhang in September and Michael Ware in October 2021. We also have a really popular program, the ECS webinar series. Our next webinar is scheduled for May 26th with, I know her name is Jill, but it's not on this list. But if you want to learn more about ECS webinars, you can go to electrochem.org/webinars. And then in-person opportunities to connect and digital opportunities to connect. We have the ECS biannual meeting that was scheduled to be in Chicago. It's the 239th ECS meeting with the 18th International Meeting on Chemical Sensors. It is digital, registration is open, and registration is free for attendees. So it is no cost for you to register and have access to the digital content. We also have SOFC in July, and then our 240th ECS meeting in October, which is still planned to be in person and registration opening in July of 2021. And now I'd like to turn it back over to Corey to do the introduction for the first set of speakers.
Thank you, Shannon. And as you saw on the schedule, we're going to go in blocks of 2. So we'll have 2 panelists speak for about 10 minutes each to give you some context on their background and what they work on. And then we'll open the floor after every 2 panelists for questions from the students. So we do want to emphasize, if you have any questions, please type them into the Q&A feature of the Zoom webinar, and we'll moderate your questions from there. But first up, we have Christopher Capuano from Nel Hydrogen and Emily Rabe from Membrion to give us a general overview of what they do in the area of electrolysis and electrodialysis as it relates to manufacturing and development. So between Emily and Chris, if you're able to go first, that would be great.
Sure thing. So Chris Capuano, I'm Director of Research at NEL Hydrogen. We have several locations across the world, one in Denmark that specifically focuses on fueling for vehicle transportation, a Norwegian facility that does alkaline electrolysis, and where I am in the US, we do purely PEM electrolysis. I've been working here for 20 years and have been primarily focused on development of our cell stack architecture and all the components within. I think primarily where I focus my attention is long-term advancements that aim to improve the electrical efficiency, reduce the capital expense of the equipment to be able to enable ourselves for the emerging hydrogen markets that are out there. So it really affords a lot of different opportunities to work with national labs, a lot of different universities, and in really interesting areas of fundamental research. Being in industry doesn't necessarily mean that you lose the opportunity to work on really interesting things. We have a pretty high-powered research group here that I get to take part in. And then the one benefit that you get from being in industry is that you get a lot of the stuff that you work on at kind of a benchtop fundamental level. You often get to take that all the way through all of your development processes to actually bring it to production and get to see all the things that you're working on at a subscale level to the point where you're actually deploying this into the manufacturing department and seeing it go out into the field. You can actually realize a lot of different improvements that you've been able to essentially be a part of, which is really nice. So we do anything from 5 square centimeter, bench testing, all the way up to what our largest cell stack is, which is a 1.5 megawatt cell stack, which is 1,500 square centimeters. So the challenges associated with taking something at a very small scale to a very large scale are unique. The fundamental stuff, a lot of the actual research that takes place is certainly very challenging. Taking that and moving it from something that's the size of like a thumbnail to something that's as large as, say, a dining room table, and doing that day in and day out, repeatedly, has a lot of unique challenges as well, which is really interesting. So you get to do research, you get to do process development, and then you actually get to do release of a lot of the equipment. And then a lot of times, because you're so directly connected to the early research as well as the developmental activities to bring that into something that's actually, marketable and sellable, also makes you kind of the expert of that. And so you're always kind of tied to it in some degree. And so there's, you get to continue working on the research stuff while you help the manufacturing department if there's any issues. And if there's anything that happens in the field where there's any issues, you have to get included into that area of the business as well. So you get the really unique opportunity to see really everything that it takes, from all the developmental activities at the beginning to actually have something that's viable, is going to meet some of the cost targets that you set out for, some of the efficiency improvements that you try to establish, bring that all the way through and get the opportunity to see some major equipment going out into the field. As an example, we've been doing a lot of catalyst and membrane development, and we have essentially a next generation part that's going into one of our platforms that's going to be the largest installation in the world, at least on the PEM side, which I'm lucky enough to be a part of. And we're just about to install a 20 megawatt electrolyzer in Spain, which is going to be tied directly into a photovoltaic array, generating green hydrogen that's going to be used to generate hydrogen for an ammonia synthesis plant. So you're really starting to see a lot of the work that we're doing here go out and start to address, decarbonization, energy storage by using green hydrogen for something that's a very energy intensive process and really causes a lot of CO2 to be dumped into the atmosphere, and have a significant impact in our ability to reduce that and leave our fingerprints on these early stages of market development in those areas. I think I didn't really have much else. I figured I would just leave it for questions afterwards. But I guess just to kind of close it, the areas of research are also pretty broad in what I do, in that it's a blend of catalyst development, electrode development, membrane development, as well as all the different surrounding materials that go into the cell stack, such as separator plates, different coatings. So it's very, very broad areas that we review as well. So the work isn't particularly siloed. You get the opportunity to work on a lot of different interesting things, so it doesn't really ever get boring. I would say, I've gone everywhere from identifying materials of construction for some of our bipolar and separator plates and the coatings that would go on to those, as well as load-in reductions for catalyst, all the way up into leading some of the cell stack design activities that we lead as a company as we continue to scale the technology to meet the emerging markets.
Thank you for that overview. That was great to hear more about, Christopher. And I'll maybe let Emily go next, and then we can open up the floor for questions from the student audience. I'm sure they'll probably have questions about what you work on and what it might take to work at an organization like yours.
Yeah, so my name is Emily Rabe. I work at Membryon, which is a startup here in Seattle. So who are we? We're a pretty small company, founded in 2016. There's about 25 people. We raised our Series A last year, so still pretty new, getting going. And what we make is flexible ceramic ion exchange membranes, which has a bunch of interesting properties. Because they're ceramic, gives them advantages over kind of the more traditional polymeric membranes that are out there, primarily that it's lower fouling and has more stability in acid and oxidizing environments. And so our main kind of market that we're using these in right now is electrodialysis. So just kind of briefly, we put our membranes, which are cation exchange membranes or anion exchange membranes, basically selecting one ion type to go through. And then we have some sort of feed water that we want to take those ions out of, and we do that using our membranes and a voltage. And then you can have your product water kind of coming the other side. So working on making these big stacks. And eventually now we're kind of transitioning to selling stacks instead of just membranes. So more development and engineering there. And so right now we're really targeting some industrial wastewater as like our main application at the moment. So this is things like in semiconductor fabrication, there's a lot of wastewaters that have heavy metals like copper, but also, really acidic solutions. And so their kind of current methods of dealing with it are things like boiling the water off or just shipping gallons and gallons of wastewater to be processed elsewhere. So using electrodialysis, we can kind of offer alternative solutions. So like this is kind of our, market initially, but ion exchange membranes can be used in a whole bunch of different processes. The company was initially started with the idea of using them in flow batteries. So, and that's something we still are doing a lot of R&D on and kind of looking at in the future. So I think there are a lot of applications. This is just kind of what we're targeting right now. So just really briefly, kind of how I got here in terms of my career path. I did my bachelor's in chemistry at a small private liberal arts college in Minnesota. I did a whole smattering of different research that kind of just made me a little bit of a jack of all trades. I did, polymer organic chemistry for one summer. I did a year-long research project using GCMS to detect human scent. And then I did a summer internship at Argonne National Lab doing more material science, which then led into my gap year before my PhD. I was a research chemist at Argonne for a year, working in just a ton of different projects, ranging from magnetic nanomaterials to engine fuel additives, and kind of everything in between. So that gave me a lot of breadth. And then my PhD, I did that at UW in Professor Cody Schlenker's lab, where I worked on a little bit more specifically organic photovoltaics and photocatalysis. So that was kind of where, I started really thinking about electrochemistry because we use electrochemical techniques to analyze those systems. I also did a lot of spectroscopy. So did some stuff outside the lab too. I, especially the Torrance Tech due diligence program, as well as being a venture analyst at WRF, kind of got me interested in thinking about, commercialization and what it takes to actually take something from a bench scale to industry and to market. So that kind of also helps, with what I do now at Membrion. I primarily right now work with the manufacturing team to take something from a very small scale to a very big scale, kind of like Christopher was talking about, because our process, initially was kind of like a dip coating. And that was great when we were making, really small membranes, but now, we're aiming to make, thousands of meters squared a month. So how do we do that? And then my job is really to be the chemist there, thinking about every change that we make to scale up. How does that actually affect the nanostructure and the chemical interactions that are so important to our membranes? So it's been a lot of fun kind of being, my kind of broad background with lots of different experiences has honestly really helped me kind of fit in wherever I need to go, which is pretty standard, I think, in startup world. You get to wear a lot of hats. Because I also do bench scale research. So going back and making more very small scale stuff to try and think about new membrane chemistries or next generation products. So those were my slides. Happy to turn it over for questions now.
Okay, I'll encourage folks, if you have questions, to post them. I think I'll lead off with something that I think is important from a student perspective. And that's what each company thinks, and Corey mentioned this, is important for new hires. So what are you guys looking for in a new hire, and what types of skills can students get at different levels, and sort of what sort of degrees or do you look for? Bachelor's, master's, PhD, postdoc experience? Maybe you could speak to that. I'm sure there's a variety of answers depending on the position, but I think we'd all be interested in hearing something about that.
Sure. So I guess I can speak a little bit to that, Shannon. To your point, it kind of really depends on what the job opportunity is, right? So we have anywhere from, and you know this because we've worked with you in the past on this, we have anywhere from co-ops and internships where we give opportunities for students to come and get some of those experiences to add to the resume just beyond the degree itself, which I think has worked pretty well. In those areas, certainly for students that are looking to get some industry experience, we are generally very open to providing broad opportunity, for the students, and we're not real particular. There's enough work going on here where we always find something of interest for the students to get exposure to, whether it's in direct research or manufacturing. So as far as those opportunities go, we will post those, but myself, I always look for, recommendations from partners that we've worked with, other collaborators who have worked with individuals that they might recommend. Now, when we get into kind of the full-time employment areas, those become a little bit more specific. We'll post for a mechanical engineering position, a chemical engineer position, a research position, which is usually a grad level student. And, if you're looking for someone that's right out of school, 0 to 3 years or so, maybe relevant experience through either, laboratory work at the university or so is probably, about all you can really, ask for some degree, maybe in a prior internship in a relative, in a similar field. But the background there, we're not hugely particular. We're looking for really just, good credentials, maybe skill sets that can overlap with some of the work that we're doing, but not directly connected, where we can build some of that up. I think, one of the areas that I wouldn't say we struggle with, but we have some difficulty finding anyone that comes to us with direct, say, electrolysis experience. There's not a lot of opportunity out there to come in with a real deep resume with that type of background that we can pull from. So we try to look for experiences that you can make connections to. that look like they're similar, where they'd be able to ramp up maybe, and be a little bit more integrated and impactful on the work that we're going to ask them to support a little bit sooner. But it's a lot of the things that you're aware of. Do well in school, and try to get as many different opportunities or on your resume that you can, whether it's through internships or whether it's direct work within your lab. That's going to be able to support the field that you'd like to pursue when you get out of school.
Okay, great. And so Emily, I'll give you a chance. And there's also a question here specifically related to you and kind of working in a small startup. And from David Hurt here, how do you phrase or discuss when you're looking to join a new small company or any company, your many hats experience, because most jobs are almost never advertised as being many different hats, even though at a startup, that's likely what is required. So you probably have some experience with that, I suspect.
Yeah. So I guess the question is more like, how do you sell that?
How do you sell that, or how do you maybe respond to that? I think both those, to respond to that need or sell that capability you may have.
Yeah. I'm trying to think how to answer that. Yeah. So, I think certainly it's valuable, and selling it, I think, is just, especially if you can point out the couple things, like in my background, I had done silent chemistry, even though it was not similar, not really the same as making a membrane, but I was like, well, I know silent chemistry, and I've done all these different techniques, and I've done a lot of spectroscopy. So as long as I could pick out specific things from my very broad background and say, I never made ceramic membranes, but here are these specific things I can pull that are similar. I think that was helpful in showing that, one, I knew what they were doing, and that I could, kind of tie in my experiences and say, I think I can bring this, even if, I wasn't the world expert in exactly what they were producing. Sorry, what was the other part of the question?
The other part of the question is looking at, Membrion and your trajectory and your, hiring. How do you guys go about hiring? Are you mainly hiring locally? Are you doing, national searches? How do students, if they wanted to get involved with your work? Are there internship opportunities? How do they go about doing those? What skills are you looking for? Those sorts of things.
Great. Yeah. So definitely do summer internships. We just selected this summer's interns. So that part is closed, but we do summer interns every year. So that's something to keep an eye out for. We also will be expanding and hiring more people. So certainly keep an eye out for the jobs postings on our website. And in terms of what we're looking for, it often seems like and then whether we hire locally, I think that is, especially for the, more like lab technician jobs, that is kind of more preferred. But also backgrounds can be hugely varied. We have some people in our company that have masters in geology versus, some people that are very specific with a lot of experience in mechanical engineering or materials chemistry. So we have a pretty broad background in terms of education and field. So yeah, if you want to get involved, certainly reach out. We're always happy to chat, and keep an eye out, because I think we're going to raise our Series B soon, and then there'll be a lot of hiring opportunities after that. So
that's great to hear. So just so the students know, both the membranes that Emily's working on, they're incredibly important for all sorts of electrochemical technologies that are all sort of on an exponential growth curve right now. And then Nell Hydrogen, Proton on site, the site here in Connecticut that Chris works at, is sort of the leader in the world in hydrogen electrolysis, production of hydrogen. And that's another industry that's basically on an exponential growth curve, and will be for a while. So these are good places to think about working. There was a question from Ian Murphy about, if you're a student and you're in school right now and you have an expected graduation date, when should you start applying to jobs? When do you guys, if it should probably apply 6 months before they're graduating? Is that too early? What's the sort of matchmaking process there in your guys' view?
Yeah. So Emily, I don't mean to keep cutting you off. I hope.
No, go for it. Go for it.
So we have extended offers to students that have not finished their degree in the past, and I think that this may not be entirely accurate, but I think it's pretty close to the truth. Is most of those offers that were made in advance of a graduation were primarily extended to either co-op or intern students that, we had the opportunity to work with for a period of time prior to their graduation, knew when that date was pending, had job opportunities that we knew were going to become available, and encourage the students to apply for those, before their graduation. On our end, fully understanding that we were going to have to wait, a couple months for that to happen. We actually have a mechanical engineer that's graduating from the University of Connecticut, I guess last week actually, but he worked as an intern last summer, and we extended an offer to him in April. And so essentially we're waiting for him to graduate, take a couple weeks off after school, and is going to be joining us in early June. And so I think they're not, it doesn't happen too often, but it does happen. And so I think, that's in our experience here, that's probably been the best route in terms of actually getting a job offer or having something locked down before you graduate is tying yourself to a company prior to that. Hopefully, and that model works right now because we don't get the opportunity to really interact at a lot of these conferences right now, which is another way. And maybe that'll change in the upcoming months and year or so. But I think through our internship program, that has worked. That pathway has worked primarily through that. And I guess I just want to go back, Shannon, to your last question, because I actually have had the opportunity to be in kind of Emily's position where I've been in a startup all the way to where we are today. Because when I started this company, I was employee number 6, and we're at 400 now. And so I've had a chance in different capacities to work all along that. And I guess it's really, really tough in Emily's position, I think, to be able to pull talent, right? And just because where you are. And I think, what we've found is, a student just needs to identify a company that shares a common vision, kind of common culture. That's one of the things that we did pretty well at the beginning, I think, is, the hydrogen economy, or whatever you want to call it, it wasn't really here yet, but you can kind of see it, and you just needed to be able to paint that vision of where the company could be, and hope that you find potential candidates, students or otherwise, that shared that vision, and kind of aligned with it, and were willing to take on a certain amount of risk that you have with a smaller company, and kind of trudge through that until you can get on the other side of it. And that's tough sometimes. I think the challenge there is getting more senior people coming in at that point that may not have the same kind of risk tolerance that maybe a newer graduate might have. But I guess that's what it is. I think look for companies. I mean, if you want to be part of a startup, research it a bit. Try to find a company that aligns with kind of your vision and your values, and join them, and realize it's going to be a little bit of a bumpy ride. But I think that when you come out on the other side of it, it's a really, really interesting and unique feeling. I think, to be part of something that you really are allowed to contribute to and help grow and mature and become something of a viable company. And I think there's a lot of benefit with that as well. So with the risk also comes unique opportunity in that, because you're so lean, you got to do everything, right? And so, it gives you broad exposure. And so while I have a chemical engineering background, I primarily worked on cell stacks. Because we only had a handful of people, I had to really, really learn how to do system design work as well. And so, I got a chance to just expand beyond that and look at a lot of the full integrated kind of device. And it gives you just kind of so much more exposure to multiple areas that it really gives you a lot of, flexibility in the long term in terms of where you can be within the company.
Great. And
Thank
Emily,
you, Christopher. And I guess just to chime in, we're running a little behind schedule, so I had a quick suggestion. Maybe Emily, there was a question for you. We could answer it via the Q&A write back feature or the chat feature, and no problem. And Shannon, if you advance to the next slide, thank you. So thank you so much, Christopher and Emily, for sharing your perspective. And again, I just want to emphasize, if we didn't get a chance to answer some of your questions or continue the conversation, do feel free to leverage the chat feature, or if you have a question, we can respond to it by typing a response in the Q&A feature. But next up, we have a different focus, more focused on what it's like to work at a national lab with a focus on battery research. So we have Marco Doof, who works at Lawrence Berkeley National Lab, and Jay Shao, who works at the Pacific Northwest Lab, to share their perspective with you on the type of research they do and what their general career path has looked like. So from there, I'll let Marco go first, and thank you so much for joining us.
Thanks very much. So I'll talk a little bit today about energy storage research at Lawrence Berkeley National Lab, where I've been for over 30 years. So first I'll tell you about myself. I'm currently the secretary of the Electrochemical Society and a fellow of that society, as well as the Royal Society of Chemistry. And currently I'm the deputy division director of the Energy Storage and Distributed Resources Division at LBNL. My research focuses on materials for energy storage. So in particular, lithium-ion batteries, sodium-ion batteries, and solid-state batteries. And so I did not come to this field directly. I started at the lab more than 30 years ago, and there was actually at that time relatively little energy storage research. It was really sort of an arcane field. And I did do, I got my PhD in inorganic chemistry, and I did do some electrochemistry pursuing my graduate studies at Brown University. But I was by no means a battery expert. And I think that was true at the time, that many people sort of came in through the back door. They did organic chemistry, they did some kind of chemical engineering, they did inorganic chemistry, and it was such a backwater field at the time. And so we were all learning as we were going along, publishing papers on our research and so on and so forth. And, there just wasn't that much interest for whatever reason. And then, of course, lithium ion batteries burst onto the field, and I think it really changed our lives. I'm old enough to remember a time when, if you were supposed to meet somebody and you were running late, you had no way of contacting that person because you didn't have a cell phone. Cell phones were really rare. Doing a presentation like this remotely, not a chance. We didn't have the technology. And I think as time went on, people started to understand the importance that energy storage has on our lives, batteries. And, at the same time, there was kind of a boom in material science research with all kinds of new techniques being developed. So along the way, things have really changed. And there's been, I'd say, a boom in energy storage research and funding. When I first started, every year, we were told, well, justify your existence because we're going to zero out the budget for this. And so the first couple of years we're kind of hanging by our fingernails, trying to persuade funding agencies that energy storage really was important, how things have changed, because I think every agency in the United States, surely, but around the world, has a program in energy storage, and it's just become more and more popular. So that's a good thing. There's many more opportunities, and it's an interesting field because it's a multidisciplinary field. You can work with physicists, chemists, chemical engineers, and so on and so forth. People from all different kinds of backgrounds come to it. So Lawrence Berkeley Lab was founded in 1931. It's our 90th anniversary. So you can see here on the right, our logo celebrating our 90th birthday. It was founded by Ernest Lawrence, and his picture's down there on the lower left. And then there's another photo from the historical archives of various scientists at LBNL pointing to a model of the Bevatron. So it was originally kind of a high energy physics lab. And of course, we have grown over the years. We're operated by the University of California. We're up in the hills above Berkeley campus, and there are a lot of people who have joint appointments, teach at UC Berkeley and do research at LBNL. We have just a stunning reputation, I would say. A lot of Nobel Prizes, 14 of them. The roads, if you go to LBNL, the roads are named after the Nobel Prize winners. And our latest one is Jennifer Doudna for her work on CRISPR. And we do a lot of basic research, energy, biological, environmental science, high energy physics, computing, etc. And we have many user facilities. And on my first slide, I had shown a picture of the Advanced Light Source, which is one of the user facilities I use a lot, or synchrotron facility. There's also the Molecular Foundry and the National Energy Research Scientific Computing Center. So I'll tell you a little bit about our division. There's a picture there of somebody working in a glove box. And those of you who do research on batteries are probably pretty familiar with that. So there are various groups in our division. Of course, energy storage group, applied energy materials, energy conversion. So we do work on fuel cells and the like as well. There's a group that's involved with grid integration and laser technologies, and also thermal science. So thermal energy storage is growing. It's getting to be a larger part of our division. And, we're researching problems in transportation. Many of us in the energy storage group get our funding from the Office of Vehicle Technology. So we're primarily concerned with batteries for that. But I think we're going to be branching out more and more into the grid. That's becoming more important. And then new initiatives in water energy nexus and the science of manufacturing. We have in our division probably about 145 people. It varies, of course, it fluctuates. People are always coming and going. We have a lot of postdocs. We do sponsor the John Newman Early Career Fellowship, and we actually just recruited for that. It closed, and we're in the process of sifting through the packages that people submitted to select our next Newman Early Career Fellowship. And that's a fellowship really targeted to finding a young scientist interested in beyond lithium-ion technologies. So there's a big area called the energy technology area, and we're one of several divisions in that. There's also building technologies and energy analysis. So we work closely with these other divisions on our research. So we have a long and distinguished history of battery research at LBNL. I think we were probably one of the first to do battery work of the national labs, the other one being Argonne. And this is all due to the Charles Tobias, who is pictured there on the right. He arrived at UC Berkeley in 1947, and he showed that lithium metal could be electroplated reversibly in certain non-aqueous electrolytes. And that started the whole thing with lithium batteries and lithium ion batteries. I think before that, nobody had a clue that you could do that reversibly. And so the electrolyte was very important there. And so really, I would say he's almost the father of modern day lithium batteries. John Newman was another big figure at LBNL. Also, UC Berkeley professor who literally wrote the book on electrochemical engineering. So you can see a picture of that book also on the left. And of course, we've named the fellowship after him. So we consider him, a big figure in our research. Elton Cairns also came to the lab. He actually is still active. And he and Tobias established a Center for Applied Electrochemical Research at LBNL in 1979. And, at first it was a lot of different kinds of batteries, aqueous batteries, other types of energy storage systems. And that started the program that changed names over the years, and it finally became the Advanced Battery Materials Research Program, who funds me and a bunch of other people at the lab. So as I mentioned before, mostly Office of Vehicle Technologies, but we are going to try and start expanding into maybe grid storage as funding opportunities arise. We have a program to interact with companies in the Bay Area, in California, various places around the country. It's called the CalCharge program. It's meant to be an accelerator for battery and electrochemical energy storage research. And the idea is that startups or established companies can come work with us through this mechanism. It's run by an outfit called New Energy Nexus, used to be called CalCEF. And the idea is that it's something like Semitech, which was established for the semiconductor industry, and it's meant to move the technology forward and overcome any barriers that prevent that from happening. So they sponsor a conference called the Bay Area Battery Summit yearly, and it rotates among the other national labs that are involved with CalCharge. So SSRL, Stanford Synchrotron Radiation Light Source, Lawrence Livermore, and so on and so forth. And of course, because of the pandemic, it's been virtual, but look out for that. They have different subjects that they touch upon over the years, from recycling, beyond lithium ion, flow batteries, anything like that. So this just is a slide that shows a bunch of different collaborations with companies, universities, and national labs. It's by no means comprehensive. I couldn't fit everything on the slide, but it's just to give you an idea. We have some big companies, we have some startup companies, we have various universities. Of course, we like to work with our collaborators at other national labs. So this kind of charts out the status of battery research in our division and at LBNL, ranging from the top on something that's maybe highly high risk, high, at a low technology readiness level, but maybe would be something that would be really earth shattering if we can develop it. And those are new storage paradigms. These are things like, magnesium ion batteries or calcium ion batteries, or redox flow batteries with organic solvents. And that's funded by generally Office of Science programs at DOE. For example, the Joint Center for Energy Storage Research and various energy frontier research centers across the country. And we have people who at LBNL who are working in those programs. I'm working in one of the EFRCs, for example. And then we have the Advanced Battery Materials Research Program, which I mentioned before, which is really looking at materials for some of these new storage paradigms, for example, lithium metal sulfur batteries, or solid state batteries is part of this research. And there is also a program at LBNL on disordered rock salts. That's a next generation cathode material for lithium ion batteries, which has the advantage of being a no cobalt or nickel potentially, and very high capacity. So that's, a material that it's not ready yet, but progress is being made. So those kind of intermediate future, maybe 5 years from now, they'll be available. We do have some people involved in the Battery 500 program, which is to advance lithium metal batteries. And 500 refers to 500 watt hours per kilogram. So that's a goal. And that's also really advanced lithium ion and some lithium, lithium metal batteries, perhaps with liquid electrolytes or solid state electrolytes. And then we have programs that are more, I would say, applied or, meant to look into materials that might be ready in just 2 or 3 years, silicon anodes, extreme fast charge. So the idea there is to take a lithium ion battery and find out what limits its charge acceptance, and then make improvements so that you could charge up your battery at a charging station in 10 minutes and then be on your way. And that has, if we can do that, then we don't need such large and expensive batteries in our vehicles. And it gets rid of a lot of the range anxiety that people experience with having electric cars. And then there are some programs that are pretty heavily applied, funded, for example, by the Office of Electricity or the Advanced Manufacturing Office on manufacturing. And then, of course, as I mentioned before, we work with some companies through CalCharge, SBIRs, and so on and so forth. And the idea there is, they usually have a technology that's at a higher technology readiness level, maybe not ready for commercialization, but they want to push it forward. So, and then we do have people working in ARPA-E programs, and that sort of covers the whole range on this chart. It's oftentimes really high risk, crazy ideas that could just, revolutionize energy storage if you can overcome the barriers. And so it ranges from, new designs for lithium ion batteries to, some new kind of a redox flow battery that might be really great for grid storage, and so on and so forth.
Marcus, Corey, just to quickly chime in, I want to make sure we left enough time for Jay and some of the student questions, since we ran a little bit over. Would it be okay to maybe stop here, and we can always bring this back up during the Q&A portion?
I was just going to show some slides on my research, but I think we can stop there.
Yes, thank you so much for the broad overview, and we can always come back to this. I just want to make sure we leave enough time for some of the student questions about your work.
Thanks very much, Corey, Shannon, for leading this effort to organize the Industry Day for Pacific Northwest section of ECS. So, when Marka was talking, I was trying to update my slides to be more consistent with other presenters and share a high-level review of what's going on at the PNL, especially in the energy storage programs. So before I started today's talk, just like Marka, I added an additional slide to briefly introduce myself. So currently, I'm a lab fellow at the Pacific Northwest National Lab. I'm also the technical group manager of battery materials and the systems group. So our group, which I will introduce later, we covers a full spectrum of energy storage research, from materials to device to deployment. Our group has around 70 staff members at this moment. Yeah. I'm also a fellow of Electrochemical Society. Marka Duif, she was the past chair of ECS Battery Division, and she and Shirley, kind of identified me and found me, chose me to be the serve in the battery division as one of the 4 officers. So currently I'm the secretary of ECS battery division. I'm also the chair, founding chair of our ECS Pacific Northwest section, working together with Corey and Shannon and many others to promote electrochemistry research in Washington State, Oregon State, and Idaho State. Yeah. So I got my PhD degree from State University of New York, Binghamton. So some of you probably recognize Professor Stan Whittingham. He was my PhD advisor. He is also the Nobel Prize winner in 2019 for his outstanding contribution to lithium-ion battery technologies. So I joined the PNL in 2008 as a postdoctor, and then got promoted to scientist 2 years later. I left the PNL from 2016, between 2016 and 2017, and stayed in as associate professor, stayed at the University of Arkansas for like 1.5 years, and then came back to PNL in 2017. You can ask me why later, but to save some time, I hope I will advance to the next slide. So as a national lab, right, we definitely have a lot, you know, not as big as Lawrence Berkeley, but as a national lab, you know, we have 5,000 staff members, a lot, you know, $1.1 billion for research. Average per year. We have a lot of publications. Our main campus of Pacific Northwest National Lab is located in Eastern Washington. The city is called Richland. We also have office and sites in Seattle, Portland, and Sequim for different researches. So we are, like many other national labs, you know, one of our missions is to, you know, do great science, right? To advance our technologies, to decarbonize our environment, promote energy storage research, charge our planet sustainably, as well as enhance national security. So the largest portfolio, research portfolio at the PNL is actually related with national security. Today I will focus more on the energy storage programs at the PNL. So this slide will kind of summarize what we are doing, you know, in battery research. So we have very diversified research portfolio from, you know, batteries for stationary application to EV batteries, and then to consumer electronics. So in each category, as I showed here, we cover really a full spectrum from materials to electrode to prototype batteries, and then to the eventual deployment of the technologies that are developed at the PNL. For stationary application, what I show on the left side is about 1 kilowatt redox flow batteries using the vanadium-based aqueous electrolyte, which has been licensed to at least 7 different industry companies. So my colleagues, David Reed and Wei Wan, they gave you know, a webinar. Actually, it was the first webinar of our ECS Pacific Northwest section series. So I'm not going to talk about the battery technologies for stationary applications at this industry day. I will use how we do EV battery research and some very interesting tiny batteries for miniaturized sensors to give you a flavor of how we correlate the scientific discoveries to their practical applications and make sure industry can use them. So some of you probably already read the news about the grid storage launchpad facility. This was launched last year, well, actually early this year. So DOE's Office of Electricity has selected our lab as the site for a new national grid energy storage R&D facility that also includes investment from the state of Washington, Battelle, and the PNL. So by 2023, by fall 2023, all the research facilities, related with this slide, as well as a grid modernization and analysis, will be moved, integrated into the same building as I showed here. And this we call GSL. It is it will be a very critical technology component for realizing a modernized, resilient power grid capable of achieving many broadly shared energy objects. It will support DOE's energy storage grant challenging. The vision of DOE's energy storage grant challenge is to create and sustain global leadership in energy storage utilization and secure domestic manufacturing supply chain. Yeah, you will hear more news about the GSL, and hopefully my colleagues and myself will keep you updated on the progress of GSL. We're very excited to move into this new building and collaborate with industry, accelerate the innovation, and validate everything at industry relevant scales. So I found that many of the audiences are graduate students. So in addition to the very high level introduction, I would also like to show briefly, 3 examples of what kind of research we are doing and how we are using our, really first-class scientific tools to help us understand batteries and then redesign materials. So this is a slide I just selected from one of my previous DOE annual merit review meetings. So this is the SEM images. Let me see if I can use the laser pointer here. Single crystals of nickel rich, high nickel content, NMC cathode. Currently, the UV batteries is using lithium, nickel, manganese, cobalt dioxide with transition metal 1/3 of each. And if we increase the nickel content, you can have more capacity and energy. But the problem with these nickel-rich materials is that they detach from each other because they are agglomerated secondary structures, which I did not show here. It's like immutable. So one scientific question we ask ourselves is, instead of making those agglomerated particles, can we just use a single crystal, nickel-rich NMC, to address the cracking issue, the gas generation issue, and also the sensitivity to moisture, because all of them are, related with the surface area and the phase boundaries. So these are some images of single crystal nickel-rich NMC that we synthesized in the lab. So we use electrochemical testing as a tool to understand how the crystals respond under the electric field. So these on the left side are cyclone data at different cutoff voltages. Right? If we just cycle the materials within the normal window, so this is a lithium-ion battery, which means graphite is being used as anode. This is a full cell testing with reasonably loaded cathode materials. So between 2.7 and 4.2 volts, it's quite stable under 200 cycling, which means a single crystal is indeed probably a good potential candidate to replace the polycrystal nickel-rich NMC. But when we elevate the cutoff charge voltage, you see some gliding marks, right? And then when you increase cut-off voltage to 4.4, you see some micro cracks also form. But very interestingly, even though there are some gliding and cracking form, the atomic arrangement is not altered after this gliding, right? So to understand why we use the in situ atomic force microscope, I'm trying to find my, to understand why. So this is a single crystal. These are few, 1, 2, 3 single crystals, under the electric field. So you see the gliding is reversible, right? The plates. You can understand that this single crystal is made of a lot of building plates, and during charge and discharge, the plate comes out and back reversibly. It's not completely 100% reversible, but it does explain a lot of why we see these gliding marks, why it does not alter or change the atomic level structure of the crystals. So if you are interested in more details, you can check our published papers in Science last year. We have also DOE presentation slides online for you to get more information. So Mark also mentioned the Battery 500 consortium in her presentations. So 500 consortium is dedicated to address the fundamental challenges to enable next generation lithium metal batteries. So PNL is currently leading this consortium for DOE. 500, as Mark mentioned, refers to 500 watt-hour per kilogram. So one thing I would like to mention or emphasize here is no matter what kind of cathode you are using, no matter what kind of chemistry, liquid electrolyte or solid electrolyte, if you want to double the cell of energy of a state-of-art lithium-ion batteries, you have to use lithium metal as the anode. So that's why Battery 500 consortium focus on lithium metal battery technologies. While the cathode can be changed depending on what we need. So this consortium, PNL is leading the consortium. We have 4 national labs and 5 universities in the core team, plus 10 seedling projects across the country to support the consortium. We also have the industry advisory board who review our progress and gauge our R&D. You see the logo of Tesla, right? But also have a US ABC in the industry advisory board. GM, Ford, Chrysler are all members of US ABC. So we do have a very strong support from industry, which helped us a lot to advance the technologies. The picture on the left side is was taken in one of the quarterly review meetings in 2018. So 1 year later, 2 of our Battery 500 PIs, Professor Goodenough at UT Austin and Professor Stan Willingham from SUNY Binghamton, he was my PhD advisor. They both won the Nobel Prize in chemistry. This is really amazing, consortium generated 2 Nobel Prize laureates. The left corner slide summarizes the progress of our lithium metal battery technology in the past 4 or 5 years. We started from 300 watt-hour per kilogram and then 350. We also have 400 watt-hour per kilogram, which is on the testing. I did not show it here, but you can see the 600 stable cycling of this prototype 350 watt-hour per kilogram pouch cell is really a record cycling. This is really very exciting. Of course, we still have a lot of things to do, but just give you a flavor of our progress. Last slide just shares with you not a very applied research of micro batteries. So in the past 10 years, we have been delivering every year. We design and deliver hundreds of up to 1,000 units of micro batteries to power their miniaturized sensors. This is the sensor, this is the micro battery. To track the small fishes, such as juvenile salmon, when they pass through the hydroelectric dams, to collect the data, to evaluate the survival rate and the behavioral changes of those small fishes. If Corey give me 90 seconds, I can show this movie. Can you hear the sound? Okay, great. Yeah, that's all I have today. And this picture is one of our group's virtual seminar. We are having the weekly virtual seminar to make sure our staff members are staying connected during the pandemic.
Jay, your audio is really faint for me, but thank you so much. And thank you, Marka, as well. And I guess I sent a message. I wasn't sure if there were any questions for Marka or Jay. And Marka, you're free to pull up your slides again if you didn't get a chance to cover something before, as we see if there are any questions from the students in the audience.
I see we have a question from Cody, who Jay and Marka would like to know what qualities and experiences you look for in new hires. And specifically for postdocs, do you need to have, or if there's previous postdoc experience, is that something that can be favorable or unfavorable on a resume?
Marka, do you want to start first?
Sure. So LBNL has a policy that they will not hire someone as a postdoc who is 5 years past the PhD. So, and the requirements are going to vary with the group that is hiring. If you have a year or two of postdoc experience, I think most people would consider that to be fine. But most often I would say that we hire postdocs who are fresh out of grad school.
Yeah. Can you hear me? Because
it's quiet.
It's quiet. Can you hear me now? My God. How about now?
A little better.
Okay, so I don't know what happened. Yeah, so we have the same rules as Berkeley Lab, but that doesn't mean we don't have any postdoctors who is not a fresh PhD, right? So it depends. I mean, it's still the expertise, technical background, and the passion of the individual that will help the interviewers and the program measures to make the final decision. We do have postdoctors who had a prior experience of research associate in certain universities or even other labs.
Another question we had is related to students who might not have already worked at a national lab or have sort of direct ties to someone doing research at a national lab. Do you have recommendations for those students in terms of how to sort of make their name known and when they're applying?
Yeah, so I think, Marka, I will start first, if you don't mind. I think today's industrial day is a great example, right? You go to the professional society meetings, get to know more people. But when I talk about the normal people, that doesn't mean, just have a lunch or dinner with someone and they don't know what she or he is doing and what his background is, right? I mean, you have to read people's papers, right? Understand what they're doing. And then if you meet with them in certain professional society meetings or workshop, don't be shy. I think I did this to Marka, when I was a graduate student. Well, Marka is, kind of a role model indeed for female scientists in our field. I know Marka for a long, long time, and she always provides the strongest support. I know all Marka's research. I follow her papers. If you want to join any institution or especially interest in certain PI's work, you should follow their work, right? Read their papers. Right? So this is what you do decided if people will know you.
Sure, I would just say, if you're interested in working at LBNL, go to jobs.lbl.gov and there'll be listings there. And you can look and see, I get people applying and other people get people applying, and we don't necessarily know who they are, but if they have an interesting looking resume, that's relevant to what we're looking for. We don't necessarily have to know that person. So, it's nice to have an in. I would say it's not always necessary. But, I would do as much networking as you possibly can, given the constraints of the pandemic. I know right now it's really hard, but certainly I go to ECS meetings and talk to students there. That's, just if you have the opportunity to do that, is to certainly go up to somebody, whose research you're interested in and start a conversation. I'm always happy to do that if I have the time and I'm not racing off to some other event or meeting or something like that. But, rest assured that if you've been active in, say, energy storage research and you've published some papers and you've given, a talk or a poster at a conference, that's a good way of getting your name out there. And you don't necessarily need to be known to the people who are doing the hiring at LBNL. I've hired lots of people that, I didn't know who they were until, their application landed in my inbox.
Yeah, so my colleague, Dale Walker, he also put in the website of PNL jobs in the chat box. You can also send Dale Walker, he put his email in the chat box as well, for information about the jobs in our lab as well. Thank you, Dale.
And I'm just going to chime in quickly. We're about 20 minutes behind schedule. I apologize to everyone, but there is one question in the Q&A. Marka and Jay, if you maybe could answer it, or Paul can answer it on your behalf in the chat feature, that would be great. But thank you so much for sharing your perspective on what it's like to work at a national lab. And to echo what's been said, I do encourage everyone to join the Electrochemical Society. That's a great way to interact with some of the people that you see on the panel today, as well as kind of get your introduction into the field and start networking more with people. But with that, thank you so much again for sharing your perspective. And Shannon, if you could project the next slide for our next two panelists. So we just had the national lab perspective on battery research. So now we're going to shift gears a little bit. We have Craig Owen, who works at Microsoft, and John Trella, who works at Boeing. And they're going to also talk about batteries, but more with the perspective on commercialization and end product applications. So with that, Craig, if you're ready, thank you for joining us today. I'll let you take the floor.
Sure. Hopefully everybody can hear me.
We can hear you just fine.
Great. So yeah, thanks for the opportunity to talk to everyone here. I know it wasn't that long ago when I was kind of doing a similar thing, trying to kind of talk to industry people and learning about how industry worked and things like that. My name is Craig Owen. I'm a battery development engineer at Microsoft. So yeah, I'm the kind of end OEM, make a device kind of perspective when it comes to battery technology. So we work on kind of all the devices in Microsoft that run batteries outside of the kind of cloud Azure team and data centers. So we work on all of the tablets, laptops, accessories, basically anything with the battery in it. We have kind of a hand in the development and design of that, as well as characterization and kind of qualification. So I just kind of wanted to talk generally about the kind of roles that we have in battery development. So we kind of talked a lot about the different opportunities that kind of these careers have. But in battery development, especially at Microsoft and a lot of OEMs, there's a lot of different roles that you can have that you can actually work with batteries. So maybe it's traditionally thought about as kind of an electrochemical focus, but there are a lot of other disciplines that kind of have a hand in battery development. So we have system engineers, electrical engineers, mechanical engineers. They're all kind of working on different parts of the battery in terms of its integration into a product. And so there's a lot of different disciplines that kind of come together and work. And I would say that development is kind of focused on creating a product before it enters mass production. But there are a number of other battery teams at Microsoft that are doing specific battery work. So we have a safety team, we have a reliability team, we do some validation engineering work, and then we also have program managers. And so each of these kind of groups end up having a piece of battery. So for those who kind of are thinking about what a career might look like and what's the background, I'd say that there's a lot of different ways you can kind of get involved with batteries, especially as a kind of end OEM. So I kind of just wanted to talk about that forward in terms of where they kind of interact with the product. So especially at Microsoft, I like to think about our group in development as a startup mentality at a large company. What I mean by that is there was a lot of discussion earlier about how you need to be an expert in a lot of different fields in a startup and how your knowledge is kind of expanded by wearing a lot of hats and doing a lot of different jobs. And I would say that that's very similar kind of in what we do in our group. There's a lot of different backgrounds taking part in a lot of the different steps in building a battery and for a device. And so kind of at the highest level, we have the final product, and our battery system engineers and mechanical engineers have to kind of work with that team to define the product and its requirements and whether the battery can fit in it. And then when we talk about the next level of the battery pack, we kind of have everybody's input. So we have electrical, mechanical, chemical engineers, material sciences, all those kind of people are involved in the pack side. We do the protection circuit in the battery management system. We typically focus with the system engineers and the electrical engineers, and then kind of at that smallest component, the battery cell, the electrochemical part, we kind of focus with the obviously cell engineers, battery scientists, and then mechanical engineers are also heavily involved in making sure that the dimensions are correct for kind of fitting in a device. So I'll say it a lot, but it's a very kind of cross discipline, kind of cross development type field. So you don't end up kind of going into a single area and then kind of being stymied there. And so just to kind of give a very high level description of kind of the process that you would go through in a commercial setting. So we would kind of go into a design concept where we'd work with an industrial design team. We come across a new product or a new category. The industrial design team comes to us and says, hey, you know, we have this idea for a device. We need some requirements from the battery. We need a certain runtime. We need it to fit in this certain dimension. And the system engineers kind of work with that team directly. And I put requirements iteration as kind of a major step in that, because often what happens is what we're being asked to do is really difficult or maybe even impossible with the current battery technology. And so there's a lot of iteration about, well, I wanted, 2 days of battery life and I want it to be really, really thin. And so I need to kind of have, there needs to be some interaction and iteration with the teams to kind of land on a final design that's really producible, mass producible, in order to make a good product. And so once we kind of landed on the requirements, we approach a vendor. So we're not a manufacturer. Microsoft doesn't manufacture batteries, but we approach contract manufacturers overseas, directly kind of making the components, the circuit boards, the packs, and the cells. We talk to them, we select kind of the suppliers, and then we actually go into some build prototyping. So in this stage, we'll actually build all the components, the cells, the circuit board, the pack. We'll do the assembly. We'll actually make the final product and do a bunch of characterization testing. We'll learn a bunch of things about the design, where we need to improve it, and we'll go back and we'll build another version, prototype version, and do the same thing again. And this is where we typically travel. So we typically travel overseas, go visit the manufacturer, kind of go onto the manufacturing line, learn a lot about how these things actually are built, kind of do quality checks, do control checks, things like that. And once it's kind of gone through all these prototyping phases, then it kind of enters mass production. And at that point, the battery dev team at least kind of hands that off, and it kind of has entered mass production and our stage is kind of done. So since there's a lot of academics and people in here, I know one thing that really excited me was like characterization equipment and what can you actually do. And so Microsoft and a lot of OEMs, they have test equipment. They're not just kind of a sit behind a desk type job. There's a lot of actual testing that our facilities in Redmond, and we have a number of kind of regional labs as well. We'll actually go to the lab and test this stuff in equipment that we own. So we have thousands of channels. We have thermal chambers. We do HPC. We have FRAs, glove boxes, kind of all the standard stuff that you would see in a lab. We do all this stuff, and we have it available to kind of do characterization work on batteries. So when we do this kind of work, we're really trying to simulate the device usage for users. So are they actually charging and discharging their batteries? Do they kind of keep their battery plugged in all the time, on their desk when they're working from home? Are they kind of charging it up at night and then using it down during the day? Or are they just kind of letting it sit on a shelf in storage? So all these kind of conditions, we have to do a bunch of testing to make sure that when a user ends up purchasing that device and using that device, that the experience is expected and it's a good experience overall and it's reliable. So this is an example just of like one of our non-contact scanning equipment that we use to kind of take the three-dimensional size of the battery so that we can understand how it changes over time. And so my journey for industry and into industry started back in 2009. So I actually built an not EV, but an e-bike back in high school for the kind of Washington State's kind of senior project. And that's when I really had to learn a lot about batteries, and it was all like lead acid and LFP at the time. And it was really expensive or really heavy. And I thought, wow, there's gotta be some middle ground here. And so when I went to college, I actually studied material science with the direct intent to actually work on batteries. So it's kind of maybe in a weird place where I kind of knew in high school what I wanted to do in my career. But not a lot of people kind of run into that scenario. And it just so happened that batteries ended up becoming kind of a really hot commodity in the kind of current market. So in college, I went to Washington State University. So for all the people at UW here, bear with me. But I went to Washington State for 4 years, got a degree in material science. Then I went to stay actually there for my master's degree and my PhD. And at that time, I did some work on tin anodes for lithium batteries. And then I was also kind of a NDSCG fellow during my time there. And kind of in the last year or so of my graduate school, I started a company working on silicon anodes, and we spun out as kind of I was the CTO and the CEO for a while. And I did that for about a year before I started as a contractor at Microsoft in 2018. At that time, I worked specifically on kind of building their characterization lab and working on characterization for the products and things like that. And in 2019, I've kind of joined more as a full-time employee and worked a little bit more on the product development. So working on devices, cell design, that kind of thing. Now I run our technology qualification program. So for our next generation batteries, I run the qualification program. And I'm also involved in all of our partnerships and programs with third-party companies like startups and academic labs and things like that. I'm kind of the new technology scout and working on some of that stuff with them. And so finally, just to kind of wrap it up, who we kind of look for. We kind of look for everybody who kind of wants to work on batteries. There's not really a limit to that. I would say that we're looking for people, in mechanical engineers, electrical engineers, electrochemists, et cetera. Specifically, some of the things that we're looking at right now are in the area of like modeling. So computer modeling for battery, BMS design, or just cell modeling, performance modeling, et cetera, as well as kind of just battery sciences in general. We have a lot of characterization equipment that we're trying to kind of get on board. And so those are kind of just two general areas that we're kind of looking at right now, but positions in all of these areas are kind of opening randomly. When I started in the group, I think we had about 10 or 12 people, and over kind of a 2 or 3 year period, I think we have like 30 plus. So we've been growing a lot, and I hope the team continues to grow over time. So anyway, that's all I have. Thank you.
Thank you, Craig. That was great to hear more about what you work on at Microsoft, and to also give you a bit of a plug, your company's hosting a recruiting session this afternoon from 1 to 3 p.m. Pacific time. And just to let everyone know, you should have gotten an automated message from the Electrochemical Society with the Zoom or Microsoft Teams access for all the afternoon events. So do check your email that just went out. But with that, I'll let John take the floor to talk about what he works on at Boeing, and then we'll have some time for Q&A from the audience. So just as a reminder, if you have any questions for either of our panelists, be sure to put them in the Q&A feature.
Okay, thanks, Corey. Can you hear me okay?
Hi, I can hear you great, and I can see your slides.
Okay, great. Hi, my name is John Trollo. I'm an Associate Technical Fellow in Electrical Subsystems at Boeing Commercial Airplanes. I wanted to give a quick introduction. Actually, is this in the way for my screen? You can see the slides, okay. What batteries on airplanes are and what type of batteries we use. So for rechargeable batteries, we use nickel, cadmium, lead acid, lithium ion. I have a picture over to the right of a main APU battery that's 28 volts. Every airplane has one. 787 is the only one with lithium ion. The rest are all NiCad that we currently produce. And it's used for backup power in the system. And it's also used to start the APU on the ground or in the air in case of an emergency situation. We also have some rechargeable batteries for emergency lighting. So in a situation where the lights need to come on the airplane, we need a backup power system to do that. And there's also some in-flight entertainment systems that have tablets. So rechargeable batteries like lithium ion or pouch cells in the tablets. In non-rechargeable, we actually have quite a few non-rechargeable batteries on the airplane. And some of you are probably familiar if you've ever heard of like the black box, or for example, there's a picture down below. It's actually orange. It's the flight data recorder and the cockpit voice recorder. There's a small battery in there that's a beacon, the underwater locating beacon that pings if there's a crash in the ocean that investigators can find the site, and there's a lot of data in there, and it gives them a lot of information that they can evaluate and to find out what the root cause of the accident was. We also have emergency locating transmitters. So if you're ever on the airplane, you're back in the galley, you can look around the galley, and sometimes there's an orange box that's mounted to the wall. That's a portable ELT. So it's a similar situation where if there was an accident, when you flee the airplane, the flight attendants would grab the ELT, and there's an antenna, and they would turn it on, and so the passengers can be found in the case of an emergency. Also, we have small batteries on some of our electronics boxes that are used for memory holdup. So that's kind of a broad scope of the type of batteries that we have on our airplanes. And the next I wanted to, since this is for future applications, I wanted to talk a little bit about some of the key requirements and some of the things that we're looking for in the future for hybrid electric and all electric application. Most of you are probably familiar that like eVTOL and hybrid electric is actually gaining a lot of traction. There's a lot of startup companies. Boeing is definitely interested in this area. We acquired a couple years ago Aurora Flight Sciences. And so they are now part of the Boeing company and working on eVTOL. We also have a joint venture with Whisk. And so we're working on a eVTOL application called Cora X. And so in the future, some of these applications are very unique and they require high voltage. And some of the systems, it could be up to 1,000 volts or higher. We also have a very aggressive target for specific energy density where we would like to have cells that are greater than 500 watt hours per kilogram. Some applications really require greater than 500 watt hours per kilogram. So down at the bottom, there's a picture of Sugar Volt, and that's a Boeing study that was completed for NASA. And I think to make some of the business cases closed, we had to reach 700 to 750 watt hours per kilogram at the cell level. So it's approximately, 2 to 3 times, closer to 3 times higher than the current specific energy density of cells today that are commercially available. We also would need high packaging efficiency. So if the cells are really light, but then they have to be packaged in a situation where it becomes very heavy, then overall at the airplane level, that's not good. So we really need to have efficient packing. And then for us, one of our key in almost every battery installer is safety. And eliminating thermal runaway and some of these new applications, we have to have high voltage protections. They're very, very critical. And finally, one of the key areas that need technology improvement are the life cycle cost. So for these applications, the batteries really need to be affordable. So they have to be inexpensive in the initial cost. Charging them has to be cost effective. And the life, if you have a system that's only 100 cycles and you have to replace the battery every few days or every couple months, that could be a problem for your business case. So there's a lot of challenges that need to be overcome for these newer applications to be implemented. So, and fortunately, there's a lot of companies that are trying to push these technologies to achieve some of these goals. And so for us, another key differentiator from other applications is for safety and certification. So I mentioned all applications, the safety is important, but for us specifically, continuous safe flight and landing. So if you look at some of the VTOL applications, if the battery fails, that is your propulsion system sometimes. And so you need to be able to get to the ground safely, and the passengers need to be able to get off without being injured. And so that's a key thing that the regulators are working with the Jobies and the Uber Joby and our Aurora Flight Sciences and Whisk. Those are the type of challenges that they're trying to address. Also, as most people know, the battery failures can lead to a significant amount of heat. The smoke can overcome the cabin. The toxic gases can be a challenge too. So the FAA has levied special conditions which need to be met for for Part 23 and Part 25. What that is Part 23 is usually general aviation, small airplanes. Part 25 are your bigger airplanes. And for the Boeing company, we mostly are in the Part 25 area. But they do have regulations, similar conditions for other applications like helicopters. And eVTOL is they're in the early stages of the regulatory development, the special conditions and rules development. Also, we currently have an industry standard called RTCA D0311A, and this standard, which is levied for certification activities, requires that you put a battery into thermal runaway. And so it's essentially a containment test where all the cells need to go into thermal runaway. If for these future applications when the batteries are, 100 kilowatt hours or so, this is essentially really difficult. I don't want to say impossible, but it's nearly impossible to pass that test. So coming up with a new industry standard is going to be very critical, and how you do the test and levy the thermal runaway requirements is going to be critical for success. And then briefly, I just wanted to talk about the need for some of the future technology trends. The current conventional lithium ion is most likely to max out around 350 watt hours per kilogram at the cell level. And so there are some technologies that are getting close to being in mass production, or some of them are actually being introduced that are getting cells closer to that 350. We are interested in tracking some of the high specific energy density R&D, so the lithium sulfur cells, silicon anodes. We've heard about metallic lithium anodes, and even lithium air batteries. We also have been following fuel cell technologies, and we've done quite a few studies. We had a small demonstrator back in 2007, 2008. So we've been working the various energy storage technologies for quite a few years. And my last slide is just gonna talk about my career path. And so I'm a chemical engineer. I have a Bachelor in Science from University of Cincinnati. I graduated in 2000. One of the key aspects of my program at the University of Cincinnati is we had co-oping. And so it was a 5-year bachelor's program where we graduated with a 1.5 years of work experience. So my first co-op was at Copeland Corporation, where they produce air conditioning compressors. And so I was in a lab environment. I worked on materials compatibility as they were switching over from older refrigerants to new refrigerants, and the compatibility with the various parts and the oils. And so I had to do a lot of fundamental research on the materials, different temperatures, different environments. And so that job helped me get my next job at United Technologies Research Center, because I worked for someone who was very famous in the ASHRAE industry. And when I interviewed for the United Technologies Research Center job, they also owned a Carrier. So if you're not familiar with United Technologies, it's now actually part of Raytheon Technologies. So there's been a lot of aerospace companies that have been merging over the years. But my point was, you always want to do a really good job at your one job and learn as much as you can and have your connections, because you never know the next job it might lead to it just based on one experience. So that job at United Technologies Research Center, because the hiring manager knew my manager at Copeland and knew the way that his personality was and that I was successful there, she felt confident that she could hire me at in Connecticut. So I actually spent a year in Connecticut, and I got to work on a lot of really fun projects. United Technologies has it ranges from elevators to fuel cells to engines for Pratt Whitney to spacesuits. And so I worked on CO2 reduction in spacesuits. I also worked on fuel cells. And my job experience there led to getting hired full time at their fuel cell division, which was United Technologies Fuel Cells. It's changed names several times. I went to UTC Power, and then I think they're still around in some form. They were bought by a Korean company, and I was a systems engineer there. I worked on gas reformation for fuel cells. I also worked on a large 150 kilowatt PEM fuel cell, and that led to I switched groups and worked in the fuel cell stack. So I did a lot of R&D on durability and validation engineering for automotive. All of those experiences helped me get my job at Boeing Research and Technology, where I didn't work on any battery systems up until that point. I just had fuel cell experience. But they felt confident in my abilities when I came in from my fuel cell experience to transition to battery R&D. And from there, I worked on multiple programs. I also took a stint in the environmental performance group where I focused on sustainability. And I came back to battery engineering, and I support multiple programs now. And I also got involved in the industry committee for ITCA. I chaired the Special Committee 235 on non-rechargeable batteries. And I want to highlight that. That's a really important, groups like ECS, SAE, RTCA for the aerospace application, and I became an associate technical fellow in 2018. So that's sort of a general my career path, and hopefully I didn't talk too long and I can answer some questions.
No worries. Thank you for sharing all of that, John, and same to Craig. It's nice to see more of the end application considerations for batteries. And with that, we do have 2 questions in the Q&A window for, I think, Craig. I'm not sure if John, you have one yet, but I'll let Paul take it from here.
Okay.
Yeah, Craig, we have a question from Jeremy Hitt. He was wondering how your day-to-day tasks at Microsoft look different from what you did in grad school, and how often you're still able to do experiments.
Sure. So I would say, especially when you come in to kind of a company like this, especially with a technical background, the primary impact that you can make day one is kind of in the lab kind of characterization, things like that are directly transferable from what you did in academia. And then you kind of develop these kind of larger, more soft skills in program management and kind of working with other system teams and things like that. So I would say day to day for like the first year and a half, I was basically in the lab every day. That was like setting up equipment, running tests and batteries, doing data analysis, that kind of thing. Working on building the capabilities that we had. And then after that, I kind of worked kind of in a hybrid role where I worked in an office about 50% of the time and in the lab 50% of the time, working more on the upfront design that you really need to kind of be thinking, working with these other programs for a design application rather than kind of in the lab testing. But then as soon as kind of your program comes in and it's built and prototyped and it comes into the lab, then you're kind of responsible for testing it and working with the lab staff to kind of make sure that it gets tested and built. So even now, I'd say COVID has kind of made the lab life a little bit more difficult, but our lab's kind of opening back up now. And I'd say I spend, I don't know, maybe 20, 30% of my time going in the lab. I don't have the same level of day-to-day work in the lab, mainly because some of my priorities have gotten a little bit more higher level over the years, but it's always there, and any one of our engineers can basically go to the lab and run a test or run a bench experiment at any time if they think they need to do it.
Corey, do we have time for another question?
Yes, I was going to say maybe ask the one question that's left behind, and I'll shift gears to Mallory and Jerome just because we're running a little bit behind and the afternoon sessions are going to start. But again, everyone, thank you for all of your participation. After we ask this last question, if you still have any others, feel free to use the chat feature with the panelists.
Yeah, so the other question we have is just regarding potential applicants who have training in a more fundamental discipline, and how can those students sort of emphasize their other skills to prepare themselves for a more applied position, like the work that's being done at Boeing and at Microsoft.
You're gonna take that,
Yeah,
John?
I can. Yeah. Okay, I can go first. I guess one of the things that's important when you look at a job rec, you want to tailor your resume to highlight specifically what they're asking for. So there's a lot of usually soft skills that are built into the job rec, and you want to hit those points. Often, some of the applicants, when we're filtering through the resumes, they tend to just kind of be a copy paste, and you send your same resume to everywhere. And you can notice it as a reviewer. And so you really, really want to tailor it, and you want to make sure you read every line that they're asking for the job. Because a lot of times you might make it through the first filter, but when you're reading them, you can see, well, I wanted this, and this person doesn't have any of that criteria. So you just want to kind of make sure you read the rec and then highlight where you think you have your best experience to meet what they're looking for. So.
Yeah, I would say I would definitely second that for sure. There's a lot of people nowadays with very similar technical backgrounds, especially coming out of school. And often really what makes the difference in a candidate is some of their more soft skills and how they work as a team. I know when I look at people and interview people, we often look a lot about how they will integrate into a team. You know, do they have kind of the ability to speak up? Are they confident in their knowledge? Are they, you know, working with other people well? And some of those things are obviously really hard to highlight in a resume. But once you get to that opportunity where you can actually talk to somebody, whether it's over the phone, on a call, or actually meet them in person, you really learn a lot about that candidate and what they can bring to the table. So my recommendation has always been, whenever possible, when you're building a network, is to try to reach out and actually talk to those people in your network. More than just kind of having an email conversation. That's a great way to kind of get in contact with somebody and kind of get an introduction. But as soon as possible, and if they're willing to do it, you know, have the conversation, because I think that that's really when you start learning both directions. What kind of a work environment is this person working in, and then also what kind of a candidate is this, you know, potential one? Do they have these kind of soft skills and the knowledge that you're really looking for on your team?
Thank you again, John and Greg, for, oh, sorry.
I was going to add one other thing. Can I just add one thing?
Oh yeah, just be mindful of time for everybody.
Okay. Yeah, real quick. Also, if you can find out, if you do get to the interview, find out if you have any connections with like the type of interview that they have, so you're well prepared when you have it. I know at Boeing, we do a specific STAR structure interview. And so I would just Google a STAR interview, and so you can understand, so you're prepared, because often people will fall on that part when they get to the interview and they just don't understand how they're supposed to answer the question. So it's really critical. So I just wanted to add that. Thanks.
Well, thank you so much again, Craig and John, for your time and sharing your perspective. And Shannon, if you could pull up the slide, and apologies again that we're running over time. We have two panelists left. We have Mallory Miller from Moses Lake Industries, and we have Jerome Bauta, who's going to talk about his work at Gamry. And I will also plug for Mallory. She's going to give a more in-depth talk today at 12 p.m. Pacific. So if you don't get a chance to ask Mallory some questions, she will have a full 1-hour session very shortly. So I just want to promote that as well. But Mallory, I'll let you go first. And thank you so much for participating and waiting.
Thank you. And thank you for having me as well.
Feel free to go. I can hear you just fine.
Okay, so I'm going to start off just talking about my career path, actually. So as an undergraduate, I had 2 experiences. I participated in the cooperative program and was able to do research on microbial fuel cells at the Technical University in Denmark. And then my second experience was at Denora Tech, working with chlorine and bromine electrolysis cells. And it was kind of these 2 experiences that solidified my interest in electrochemistry, which then led me to do my PhD at Case Western Reserve University. And my research focus was on redox flow batteries. And that's actually very different from what I'm doing now as the R&D manager at Moses Lake Industries. And I'm at the Advanced Research Center, which is located in a suburb of Portland, Oregon. And I'll talk to you guys a little bit about my current research, which is electrodeposition for semiconductors. And I also just included a photograph of myself cycling. Something I like to do in my spare time is I actually, before COVID, was a competitive cyclist racing at the professional level. And this is just one of my favorite roads here in the Pacific Northwest behind Mount St. Helens. So just an introduction on electrodeposition for semiconductors. And I apologize if I'm going through this quickly, just for the sake of time. But just an overview, so what's kind of driving the industry for computer chips, and computer chips are incorporated in all types of commercial and industrial applications, ranging from cell phones to autonomous vehicles and smart home appliances. The key driving force for the industry right now is to get smaller, more energy efficient and powerful devices. So you've probably all heard of Moore's Law. It's basically an observation that the number of transistors on a chip doubles every 2 years. So again, just each technology node focusing on getting smaller sizes to cram more transistors onto a single piece of silicon. And actually earlier this week, IBM announced that they are producing chips with 2 nanometer nodes. So when I talk about that, I'm referring to the transistor. You can kind of see a cartoon at the bottom right of this slide. So where our work comes into play is forming the copper interconnects for the integrated circuit. So each of these transistors, you can see at the bottom of this image, you have to make copper wire connections to all of the transistors. And as these transistors get smaller, the copper wire connections will also get smaller. And I just wanted to mention, so I said 2 nanometers, 7 nanometers is also fairly common right now, but exactly how small is that? Just for kind of a scale, a piece of human hair is about 100 microns in diameter. So if you compare one of these copper wires to a piece of your hair, that would be equivalent to comparing your hair to a redwood tree. So these things are very, very small. And there's many different layers that make up the integrated circuit. So in these schematics here, you can see there are about 5 layers in the cartoon and then the SEM micrograph. Each of these layers, you have to be able to fill with copper and have a void-free fill. And this is achieved by using additives. And it's called superfilling or bottom-up filling. And you can see an example schematic here. And the way this is achieved is by using additives. So one of the important additives is the suppressor, and this interacts with chloride to block sites on the surface. So it hinders the copper plating kinetics. So it forces deposition to occur in the bottom of the feature, since the suppressor molecules are quite large and slow to diffuse. The second additive that's used for copper plating is the accelerator. So the accelerator tends to displace the suppressor, and this also accumulates at the bottom of the feature, again, allowing for copper deposition to fill from the bottom up. The last additive that is commonly used is the leveler, and the leveler just acts to absorb on sites where there's increased current density, and so this helps to smooth out the surface. And this is helpful for when you're going to add the next step or the next layer. You want to have a smooth surface before doing so. So the images I have here, the top image shows a system that was plated with no leveler, so only suppressor and accelerator. And then the bottom image, you can see there's a nice flat surface on top because the leveler was present. So at MLI, we develop not only these additives for copper plating, but we also develop the electrolytes. And I've kind of used damascene as an example because that's what my work focuses on. So the smaller features that are closer to the transistors. But we have a range of applications from through silicon vias to the packaging level plating applications. And just some of the things that we are interested in studying would be electro and electrolysis deposition, looking at the mechanisms for copper deposition, as well as like nucleation, and corrosion is also an important property as well. So we're really looking for a variety of careers and backgrounds, from chemistry to material science, and then of course engineering. So the research that we do at MLI ARC is heavily research-based. So I would say having lab experience is a huge benefit. Even if your background isn't electroplating, as I mentioned, mine initially wasn't either. But I would say having laboratory-based experience, hands-on experience is very important. And I can also post the link into the chat, but we have a couple positions currently open on our website. One that deals with plating research. The majority actually deal with our battery research at MLI ARC. And then we also have, I believe, 2 positions currently open for the wet etch work. So thank you for your attention.
Thank you for sharing, Mallory. And Jerome, if you're ready to go, I can let you go, and then we can ask some questions on behalf of the students after you talk.
Sure. So my name is Jerome Babauta. I got my PhD in chemical engineering at Washington State University in Pullman, Washington. I started my PhD looking at wound biofilms, or certain aspects of wound-related bacterial biofilms, and at some point, my PI he got a project dealing with electron transfer in biofilms, and since then I've kind of jumped on the electrochemistry kind of bandwagon, and I've never looked back. And I think at that point, I learned that I had a particular passion for electrochemistry, and that was kind of like my guiding light, I guess, in terms of research. And then I went on to do a couple of postdocs, but then ultimately I ended up joining GAMRI. And this is my one slide. So GAMRI Instruments, we were founded in 1989. The headquarters is in Warminster, Pennsylvania, which is just a little bit north of Philadelphia. And we now have remote locations across the US. I myself work remotely out of just south of Seattle. And we are a global presence. We have distributors across the country. And with this audience, I think most of you know who GAMRI is, but for those who don't, we manufacture precision electrochemical instrumentation and the related accessories, and that's usually potentiostats, among other things, and electrochemical impedance spectroscopy, so EIS. I am a sales engineer at GAMRI, and my day-to-day role is to simply talk to people, whoever contacts us, about electrochemistry. And for me, that aligns with my passion. So if you've talked to me in the past, that's great. I love to talk about electrochemistry, and I never realized before joining GAMRI, I had only focused on bioelectrochemistry. And after joining, I realized just how wide and how many experts there are out there. We've touched heavily on the batteries, battery electrochemistry, some electrodeposition, but with GAMRI, I've been talking to people about electrosynthesis and electrochemical sensing, and medical device testing, and also just generating electrochemical standards. There are folks out there and companies, both small and large, that exist that I know are looking for, new hires, graduate students coming out. So I would really encourage people here, students attending, to do your best to kind of find these people. It's hard. Before joining GAMRI, I was also looking for a position, and knowing who these people are, it's difficult sifting through a lot of the job recs and job applications. The one thing I'll say is everybody has a corrosion concern or a corrosion problem. And the batteries are hot, but a lot of times when you put a battery into a certain type of environment where it contacts water or any kind of aqueous or any kind of solvent with electrolyte, there's a chance for corrosion. And so there are a lot of folks looking at electrochemical corrosion testing. And in a broad way, electrochemical testing is faster, especially when in regards to corrosion, than other traditional corrosion tests, such as just simple exposure testing. And so, you know, I just wanted to kind of point that out. With Gamry, you know, we focus heavily on, you know, in basically implementing what our customers want. So my role as a sales engineer is to reach out to researchers, engineers, scientists, figure out what they need, what they'd like to do, and see if we can do it. And that involves a lot of electrochemical know-how. So I have to be able to ask the right questions and also highlight certain things that might be of concern that perhaps, you know, that person who I'm talking to didn't really think about it. And so, you know, that's kind of my role, my day-to-day role. And I know we're kind of running behind time. So what I'll do is I'll just put out my contact information. If you'd like to contact me through Gamry, that's my email. I'm also an adjunct faculty at Washington State University. There in chemical engineering, and I help mentor graduate students, especially when it comes to implementation of electrochemical, you know, testing and technologies. So if you are uncomfortable contacting me through Gamry, you can feel free to use my university address, email address, and also that's my LinkedIn account. So with that, Corey, and also Corey, you know, thank you for, Corey and Shannon, thank you for inviting me to talk here. I'll leave it at that.
And thank you so much again, Mallory and Jerome, for just sharing your perspective as it relates to different types of, you know, electrochemistry applications, as well as your just general career path and perspective. So with that, I'll let Paul moderate any questions that might be there. I did want to point out for, I believe, Mallory, I think you sent a link for the career site that just went to the panelists. So if you could distribute that to the attendees, that would also be helpful.
Mallory, we had one question for you about the battery projects that MLI is starting now, and I'm wondering if you could speak a little bit more about the scope of those projects.
Yeah, I'll definitely have more details on those later this afternoon. And that's not my area of research, so I really only know the basics of it, but we are currently doing research on lithium-ion batteries, and it's mainly for development of additives for lithium-ion batteries, as well as moving towards new solid state batteries, so developing polymers for those, the polymer electrolytes. Yes, I think mostly that. And then it's very specific to customer needs as well. So we're working with a couple different customers, and kind of the products that we're currently making for batteries are very highly specialized, and it's based off what those customers specifically need.
Great, thank you. We have another question, I guess, for both panelists. Just generally, what advice do you have for PhD students who are looking to go into a career that's different than maybe what their thesis field would be, or their thesis title would be?
I could start on that. So I would say, you know, be, as much as you can, an expert in the research that you have done, and be able to communicate that effectively to whoever your potential interviewer might be. I also strongly agree with what was said earlier about co-ops and internships. Prior to joining Gamry, I had actually done an internship with them and I had come and visited with them, spent 8 weeks basically getting on the potentiostats and learning about how they worked. I think if you have that baseline knowledge of how potentiostats work and can demonstrate that, that's very useful for doing lab work. Yeah.
Just to add to that, I would definitely say highlight on your research and what you've learned from it and what's electrochemistry skills you can apply to the new position in general. I think also highlighting techniques that you've developed to study your system is a pretty big key focus area, as well as here are some problems that we've run into, and this is how I worked to solve them. So highlighting like how you work through things as a researcher. Yeah, and then also just the soft skills like communication and how you work with a team are very important as well.
Great, thank you. We have sort of related, Corey, I don't know how many more questions you want to take if we're on time, or if you want to.
I see that there are 2 there. This is being recorded for those of you who have to leave early. And I guess maybe the main decision point is Mallory. I know you're giving an afternoon talk. So maybe we can take 1 or 2 more and then we'll start to close things out, because I know Shannon wanted to show a couple of more slides before we officially end.
Yeah, I guess we just had one other sort of related to the last question. If you both could comment on someone applying without a specialty in chemistry, but sort of with a past experience working in semiconductor fabs, and whether or not they would need sort of specific training in, say, material science or electrochemistry to work at your companies.
I think so that definitely depends on the position, because we have entry-level positions available, but then we also have research scientist level, so a little bit higher level positions. But again, I still think that emphasizing here are some problems that you had faced and then how you work to solve through those, and what skills you've learned from your past positions that you can bring to the table.
And I'll echo that because I'll give you my perspective from the vendor side, the instrument vendor side, is that often I will get contacted by people who have taken up a role in some kind of position that requires electrochemical knowledge or just basic chemical knowledge. And they will contact me or Gamry and just say, hey, help me out. I'm new to this. My background it's in materials, and I have been tasked to do some kind of, for example, corrosion testing. Walk me through this, please. And so I think this speaks a lot to this person because it's all about communication, knowing what you know. So that's being an expert, and then being able to communicate what you know and what you don't know. And I think if you can communicate that effectively, then you'll be successful in making that transition, I think.
Great. Thank you again, Mallory and Jerome, for sharing your perspective. And I know we're a little bit over time, but I did want to briefly just thank all the panelists for volunteering their time today. Hopefully this was useful for everyone just to gain perspective on what each of these organizations works on as it relates to electrochemistry, as well as getting their perspective on what it takes to enter this area if you're interested in a career in this field. So with that, I will pass the baton back to Shannon Reed just to close things out.
I just wanted to say thank you again for the Pacific Northwest section, Corey and Shannon putting the event together. Everyone, all the registrants should have received an email about 45 minutes ago under Corey's name with all of the login information for this afternoon's sessions. If you have issues, please feel free to email customer service@electrochem.org, and we'll get you where you need to go. If you need an example of the email, I have popped it up right here on the screen. This is what you should have received. And again, they'll be starting in a little under 45 minutes. So thank you everyone for joining today. And if you have any questions about membership, student membership, early career membership, again, please feel free to email me directly at shannon.reed@electrochem.org or reach out to us at customerservice@electrochem.org. Thank you and have a great day, everyone.